better late than never, I guess. What I wanted to do, what I tried to do this morning, I don't know what that means. But okay, seems like it's fine. I wanted to bring the rest of the formula sheet for you, or at least a portion of it, because, well, it's got the polynomials on there, which is good. It's got the quadratic on there. I don't know how useful the polynomials are. I mean, maybe, but we didn't go that deep. We kind of focused on quadratics, and the quadratic formulas on there. You can kind of ignore, or you can ignore the completing the square. I should bring this into Notability so I can draw on it. 28. Done. Let's see here. Come on. So it's got the quadratic formula on there. That's good. And then, like I said, you can ignore completing the square, but it's on there in case you want it. We have the laws of exponents, which is what we introduced last Friday, or maybe Monday. I can't remember what day, but we introduced all these laws of exponents. And then last day, so Wednesday, we talked about logs and we introduced logs. And so there's log laws that we're working our way through. And we have only talked about 2 and 3 so far. So we'll get to chipping away at those. But that's it for log laws there. So you'll have them, they're there, but let's keep going. In terms of review, we introduced logarithms. Logarithms. And I always think of my grandpa when I say logarithms, because when I told him that that I was studying math, he goes, like logarithms. I said, yeah, they're in there, but because they used to be very complicated to calculate, but now we have calculators that just do it for us. So it used to be this huge elaborate thing that you had to work through. And he's like, like logarithms. So, yeah, they're not too bad anymore. But that's because we have calculators. So anyways, kind of cute. So if we have something like 2 to the power of x is equal to 12 or some version of that, we use logarithms to solve for something in the exponent. We use logs to solve for x when x is in the exponent. And the law we use the most, maybe I'll pull it in here, is this one. And I'll bring you a printed copy, of course, of the formula sheet, but I'm not hooked up to the printer in our office, so I had to wait. I was waiting for Steve to come, but he never came. So if I take the log base b of b to the power of r, what happens is this r goes out in front. So I guess it's missing a piece. R times the log, or maybe I'll rewrite it. Sorry. Log base b of b to the power of r, I can rewrite as r times log base b of b. But log base b of b is 1, because I can rewrite this log as an exponent, right? And so here, b to the power of something equals b, right? And so here we said, let's see if it's on here. Oh, that's not what I meant, but it's what I was looking for actually, so that's good. Right, from here, we said that b to the power of a is equal to c is equivalent to saying that log base b of c is equal to a. And then I said, well, I had a hard time remembering this relationship. And so for me, what I think of is I go, this is my first loop, so b to the power of a. And then my second loop is equal to c, right? Kind of b to the power of a is equal to c. Now b to the power, so going back here, b to the power of what is equal to b? B to the power of 1 is equal to b, right? So here, b to the power of 1 is equal to b, therefore log base b of b is equal to 1. And that's just a fact, and it's on your formula sheet. So here, I want one, this one. So from your formula sheet, it's on there, it's kind of low, but log base b of b is the same as log base b of b to the 1, which is 1. Right? So what we do if we want to eliminate some base is we take the log of the same base and then we can cancel, right? That's one of the tricks that we're going to learn. But let's keep going through some examples. Did we finish this one? Can't remember. Let's see. We did. Okay. Next one then. Copy. Call this the end of the review. We're going to rewrite these in exponential form. And I always find it's easier to go this way than from the exponential form into the logarithmic form, because now I have 3 to the power of 3 is equal to 27. Right? So I have 3 to the power of 3 is equal to 27. Same thing, 4 to the power of k is equal to n, right? 4 to the power of k is equal to n. So being able to rewrite maybe something that's inside a logarithm, right? And being able to rewrite it as an exponent, that makes it easier to solve for n in this case, right? And so that's one of the ways that we're going to use kind of rewriting logs as exponents and vice versa, right? Is if I want to solve, particularly if I want to solve for something that's inside a logarithm, right? What value makes this equal to k? Then I can rewrite it as an exponent and I can solve for n, right? So another example. Comme ça. Solve log base 2 of x is equal to 4 by rewriting it in exponential form. Right? Well, using our loop, right, circular here, 2 to the power of 4 is equal to x. All of a sudden, we can figure out what x is pretty easily. 2 to the power of 4 is equal to x. Therefore, x is equal to whatever 2 to the power of 4 is. Who knows? What is it? Whatever it is. Thank you. Nice. So even though it looks bad, right? Being able to rewrite it in exponential form allows you to solve for something that's inside the log. Now the log is just a function, right? And so there is just a value inside here, and it's just a matter of knowing how logs work, right? The relationship between exponents and logs is important. Okay, now, whoops. How about another example? I've already given you a sneak preview of how to bring this x downstairs is by taking the logs, because I like to cut to the chase. But one of the things that we could have done is we could have rewritten this in logarithmic form, right? Which means that this would be rewritten as log base 2 of 12 is equal to x. And I just confirm by going the other way, right? 2 to the power of x is equal to 12. Okay, they're the same, right? For me, going from here to the log is a lot harder than going from the log to the exponent. I don't know about you, but so then I always want to make sure that I did the same thing by reversing it. And now, because we have snazzy calculators, did you ever figure out how to get the base? The different base? No? Okay, TBD then. TBA. So if your calculator is not letting you enter a specific base, that's okay. We're going to have a change of base formula, so you don't have to have it, but it sure makes it a lot easier. So you would take log base 2 of 12 to find x. Now we're just going to use our calculator. So from the calculator, and that's where my grandpa was right, is right, I guess. This would have been harder without a calculator, but we know that log base 2 of 12 is roughly 3.584962,501, which is roughly equal to x. Why what? Why roughly? Probably keeps going. Whenever I do decimals and it maxes out the decimals, I just assume that it keeps going. Oh. Yeah, I think they have a maximum of 9 digits showing or something. Okay. So then, yeah, whenever it's like this, I'm just being very picky about the approximately. Okay. Yeah. Yes, but it's not exact. The exact value is log base 2 of 12. I know. It's a little obsessive of me. That's all. You'll allow it. It's yeah, I know. Picky. But I do it so often I'll get sloppy and I'll do equals. I'm totally fine with that. But I do it to emphasize that this is the exact value and this is the approximate value. But they're the same. Okay. Good. We talked about, where's your formula sheet? We talked about the common log and the natural log last day, but let's just bring them in. So when we just write log with no base, it's implied that it's log base 10, and this is what we call the common log. And we also introduced log base e, which we write ln, and this is where I'm going to try to be good, but I just read it as log. In high school, I know they read it as ln probably, and that might be helpful, but I don't do that anymore. I outgrew it. The natural log is the only log for me. And I think it's, there are some, I don't remember who said it was pH is going to be log base 10. That's good. So that's something in log base 10. Otherwise, we usually just use the natural log. Log base e. Okay, good. Are we ready for another example, maybe? Copy. Log, it's implied log base 10 of 1000, right? Just thinking about what this means in terms of exponents, right? 10 to the power of something is equal to 1000, right? And so this is going to be equal to, and just use your calculator to find it, log base 10 of 1000 is equal to 3, right? But notice that 10 to the power of something is equal to 1000, and this is equal to 3. How about the common log, log base 10 of 1 over 100? Again, I'm just going to use my calculator. Log base 10 of 1 over 100 is -2. And you can always confirm, right? Does that make sense? Yes, because we have 10 to the -2 is equal to 1 over 100, right? 10 to the power of 2 is 100, but then the negative brings it downstairs, so it's 1 over 100. And so that's true. What if we have the natural log of the square root of e? Let's try it. The natural log of the square root of e, I get 1/2 on our calculator. Maybe I'll notice here, calculator, right? That's where those values came from. Why is it 1/2? Okay, I've got e to, okay, there's two ways that we could write this, but e to the power of something is the square root of e. E to the power of something is the square root of e. Well, e to the power of 1/2 is the square root of e, right? That's how we find square roots, is we take it to the power of 1/2 from our exponent laws, right? And so that's why it's 1/2, right? What's another way that we could have done it? Because we've already introduced the log law, is that, and when I write log like this, in this case, I mean log of any base, because all the logs follow the same rules, right? So this could be log base e, but log base anything of a to the power of k, I can rewrite as k to the k times log of a, right? That was the moneymaker for logs, is being able to bring that exponent downstairs so that we can solve for it. right? And so now what could I do? I could rewrite the natural log of the square root of e is the same as the natural log of e to the 1/2. Right? Now, this is the same as 1/2 times the natural log of e. I held out long enough. So my natural logs, I write them like this. You'll get used to it. This is the natural log.
That's how Allison do.
Just like a little, yeah, you get lazy. Okay, good. So you're used to it. You'll get used to it eventually. If we all band together and write our natural logs like this, when you're writing it a lot, right? You just want to have a little scribble. Why does this go to 1? Because this is e to the power of something is equal to e, right? E to the power of something is equal to e. Well, this is 1. So then this, therefore, you know what? The natural log of e. Now I'm curious, does Allison specify when she says the natural log, or does she just call it the log? Oh. Okay. Okay. I'll try. No guarantees. The ln of e is 1. Okay. Log. There's only one log for me. Yeah, I know in high school we were taught ln, but in stats we only ever use the natural log. So then it's the only log. But I know that's confusing, so I'm trying not to, but it almost came out. That's why I'm warning you. Okay, so then 1/2 times 1 is just 1/2. Ta-da! Ding! So 2 ways to solve it, right? Rewriting it as an exponent is probably easier in this case, right? But if you had something more complicated in the exponent here, then you'd want to use the log laws to bring that exponent downstairs. Downstairs doesn't make sense, but that's okay. Okay. I think there's another example. If we have to approximate log base 10, so the common log of 700, right? We're saying 10 to the power of something is equal to 700. I'm going to guess it's not anything nice. Log base 10 of 700, we get approximately 2.845098804. Keeps going. Let me count. 1, 2, 3, 4, 5, 6, 7, 8. Is the 2 1, 2, 3, 4, 5, 6, 7, 8, 9.
Oh, you count the 2.
Yeah, it's just how many it can show. There's only room for 9 things, I think. Or 10, I guess, with a decimal.
Well, that 0.3 one was like.
Was it? Now I'm curious. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow. Okay, okay. I'm okay with that. So it's exact then. All right, let's type it in. How can we check? 10 to the power of this should equal exactly 700. 10 to the power of 2.84509,804. Does it equal exactly 700? 2.84509,804. So you're safe. Then it's equal. Nice. Okay. Hey, good catch. All right. He's got a fancy box here. Oh. Time to officially introduce our go-to move. All right. And so here, this is the moneymaker. Can I say that? I don't know. It's how we solve for things in the exponent. So here it is officially. Okay. And so here, log base b of a to the power of r, we can rewrite by bringing the r down in front, and it's the same as r times log base b of a. Okay. And so this is how we solve for something in the exponent. We've already seen it because I couldn't contain myself, but here it is officially. So what we need to do is, if we have to solve for something in the exponent, you need to get everything that is not related to the exponent. So just the base and the exponent can be left before you take the log of both sides, right? So you move everything over and isolate the exponent and its base, right? And then you take the log of both sides. Now there are kind of strategic logs that you take because some log base b cancel with the base b and the exponent, right? So sometimes we can be a little bit clever about it, but I'll show you that it just saves us a tiny amount of time, and it's not a big deal if you forget. Let's do an example. We have to solve 5 times 1.3 to the power of x, right? This x is only on the 1.3 is equal to 10. So here we see something in the exponent, and you're going to think logs. All right. I want to solve for this x. And so, okay, I need to use logs. That's how I'm going to get that down and be able to solve for it, right? And so what do we need to do? First thing we need to do is we need to get just the exponent and the x on its own, right? Which means dividing both sides by 5. So from here, 5 times 1.3, and I'm going to bring the x inside just to emphasize that they're together and the 5 is not. First thing I'm going to do is isolate the exponent, which means divide both sides by 5. So I get 1.3 to the power of x is 10 divided by 5. Oh, that doesn't, I just didn't want it spanning so many lines, but. So I get 1.3 to the power of x is equal to 2. Okay. Good. So now I've isolated the exponent. Now what I'm gonna do is take the log of both sides. Any log will do because there's no obvious base that I should use. I'm not going to use a log base 1.3 because that's crazy. So I'm just going to use, do you prefer a log base 10, log base E, log base 2? We're not computer scientists. Are you crazy, Emily? I know. So now maybe I'll use different.
What you're saying there is it doesn't matter as long as you don't use the same as the base.
You can often we use the trick that we use the same as the base, but in this case the base is really nasty, so I'm not going to do that. Any base. So let's just use the natural log then. The natural log of 1.3 to the power of x is equal to the natural log of 2. Now the natural log of 2 is just a number. E to the power of something is equal to 2. Now it's not going to be anything nice. So we just leave it as the natural log of 2. Now what am I going to do? I'm going to use the log law. So then I can say that log base b of a to the power of r, or some version of that, is the same as r times log base b of a. So by that, I have x times the natural log of 1.3 is equal to the natural log of 2. Now I can shake out that x because now it's accessible to me. Just move this over a little bit so they're not so crowded. Because now what's our x? X is going to be the natural log of 2 over the natural log of 1.3. Which I'm just going to use our calculator. Natural log of 2 divided by the natural log of 1.3. I'm going to go out on a limb and say it's an approximation of 2.6419267796. Oops. You can do. Yeah. You can, but usually we use whole numbers, but you can. Let's see here. The log base 1.3 of 1.3 is 1, but the log base 1.3, okay, here, let's do that. So we could have used, the log base 1.3 of 1.3 to the power of x is log base 1.3 of 2. So this becomes x times log base 1.3 of 1.3, which, and that is the reason that we would do it, is because this is equal to 1. So it eliminates one of those logs, all right? So then you've got x times 1 over here, which is good, but then you would need your calculator. But what we're going to find is that log base 1.3 of 2 is what? 2.6419267796. So it doesn't matter which one you use, you're going to find the same value of x. You don't look,
I just
not
get
sold.
how if there's all these different types of logs, But they all give the same number, like how is that possible?
Well, how about we introduce the change of base formula?
I didn't mean that.
We can move between bases. Let's see here.
That was looking good.
Yeah, undo. Well, funny you should mention it, actually. So here, the change of base formula says that if you want to rewrite something in the form of log base b of a, but you have log base c of a, and you want to change the base. So here, usually how we use this is we want to change from log base c of a to log base b of a. So to change from log base e of 1.3, or sorry, of 2, right? That's what we had here. No, let's go this way. Let's go from log base 1.3 of 2. What's a good color here? So notice log base 1.3 of 2, I can rewrite, right? Log base 1.3 of 2, I can rewrite if I want c to be, we use the natural log over here, right? Log base e, then I can use, and I'm going to use log base e just for the matching for now, right? But that's the natural log, right? So log base e of 2. So I'm taking components from the first part and I'm forcing c to be e in this case to make them match up. What we did here, log base e. And so now I've got log base e of 2 over the log base c of b. Now log base c, which we're using e of b, which was 1.3, which is exactly what we had here. So that's why they're the same. Oops. Or maybe not the x, but here, that goes down there, right? And log base 1.3 of 2, so they're the same. That's kind of cool, I think. And so this is how you would use, so if your calculator doesn't have a specific base button, okay, so we use the change of base formula often, a lot. If your calculator doesn't have the log base something. Now your calculator is supposed to have it. If your calculator doesn't have a log base something of something button, right? If I want to take the log base, let's take, maybe I'll use blue. Let's take the log base 14. Let's go crazy. We use the change of base, change charge. change. Oh, I made a mess. It looks the same.
Like the rest drains or something.
That's fair. Oh, you don't like how lofty my H is. My H is really riding the wave here. Change. So here, what if we want to find log base 14 of 3? But without using the specific button, only using log base 10 or log base E buttons. Those are always on any scientific calculator, so those are the ones that you've got available to you. So you can choose, let's use log base 10 just for some. Use log base 10. So what you're going to do is you're going to rewrite log base 14 of 3 in terms of something with log base 10. So C is going to be 10. So we've got log base B of A is the same as log base C of A over log base C of B. So in that case, if I want log base 14 of 3 in terms of only a common log button, right? Then you would need to do log base 10 of 3 divided by the log base 10 of 14. And check it, make sure that they're the same, because you have your fancy button, but log base 10 of 3 divided by log base 10 of 14, I get 0.41628966639. Log base 14 using the fancy button of 3, oops, phew, 41628966639. So they're the same. Nice. So there's absolutely that workaround. If you don't have the fancy button, you only need one log button to get to all the rest. Okay. Just a little bit more work. Now let me see where this is, or if it is. I know it's on the formula sheet. It's on the formula sheet here in this format. Log base B of X, converting into some log base A that I have available to me, log base 10 or log base E, right? Log base 10 of X over the log base 10 of B. So it's on your formula sheet.
I can get the same thing now. You can put it just from your fancy log button. I can use the regular log button. I just hit log and then 14 and you shift comma 3.
Oh,
And that gives me the answer.
whoa, that's a weird setup. Usually there's like a little placeholder and then a placeholder. But it works.
So that comma is how you separate the two.
Oh, okay, crazy.
But
They
it-
must have
and it-
changed the programming or
but
something.
it works the same no matter which log button or your fancy log button that doesn't work. That's the same thing. It's very odd.
That is so strange. I think I only have a fancy log button and a log base E button on mine. Anyways, to avoid having to use the change of base formula all the time, make sure that you've got that fancy button going.
Fix
Nice. And
Yeah, it
just
wasn't-
like that.
It wasn't because I was in step mode.
Weird. Stats is like, you only need one log, buddy. The natural log. Just like that, we're out of time. What? I know. Just 10 more minutes. No. We can, but I know, no. If you have any questions, let me know. Otherwise, enjoy your long weekend.